So, good morning everyone. Myself Sachin Gupta. I am from IIT Roorkee, and today I have selected a topic called subspace and some intersection diagram of subspace, which I am going to teach you. But before moving forward to those topics, I would also like to share something about the space and what is the space, what is the vector space, and I have to majorly cover all the topics of vector space to reach to subspace some intersection. So, moving forward, first of all, I would like to tell what is a space. So space, it is a set of elements which are satisfying certain axioms. It by taking different set of axioms, we can obtain different set of different types of subspace. So what it is going it in this major, basically we have some collection of elements. Using them, we want to form some relationship between them, and so that we can go our we have to follow some certain axioms for those elements to win a certain collections. And what is its advantage? It helps us to create relations between different fields which have no relations earlier, so it frees us from the problem isolation. I would like to give a real life example. Suppose we were in class 10th, and after that we move in the class 11th, like doing for IIT JEE. But in class 11th we have so many difficult topics for which we have to already know the topics of 9th and 10th. If we do not know about those topics, we will face too much difficulty. So we have to create a relationship sub relation what we have to relate the topics of 9th and 10th for moving forward to 11th and 12th. So in this also we have to create some relation so that we can cover most of the syllabus at one, like in some time. Suppose like there is a metric space and vector space. So in metric space, what in the metric space, the points, we take some points, and the metric is like a distance. So we take the collection of points, and there are certain axioms, like if the 2 points are same, then their distance between zero. So like that we create the relationship between different set of points. Like in R2 we will have r square, so we will have x1 y1 x2 y2. In R3 we will have x1 y1 z1 x2 y2 z2 x3 y3 z3, like this. And in vector space we are going to move forward. So in vector space, it is a non-empty set of objects called vectors, on which are defined two operations called addition and multiplication. So where the scalars belongs to the field. So first of all, what is the field? Field are the elements, are a collection of elements which are satisfying certain axioms of addition and subtraction, such that if u and v belongs to the field, then u plus v will also belongs to the field, and their additive inverse, that is u belongs to f, then minus u belongs to f, and their multiplicative inverse, that is 1 minute, if u belongs to f, then 1 by u belongs to f. So these are some properties. They also follow distributive associative. So these are the properties which are followed by the fields, and the scalars should be belongs from the field. The fields can be set of real numbers, set of real numbers or complex numbers. But can be the set of integers be a field? Answer is no. Why? Because in integers only 1 2 3 minus 1 minus 2, those are there. But if we take the additive inverse of this, then what will be? It is 1 by 2. But 1 by 2 does not belongs to the integer, so z is not a field. Okay, so now we have got the good idea about the fields. So for vector space, if u belongs to v and v belongs to v, then u plus v also belongs to v. If u plus v is equal to v plus u, commutative, this is associative, there must be zero vector, Why, we will talk about this later. 0 vector must be there. If u is there, then minus u must be there, because if 0 vector is there, then sum of two vector and is u plus minus u must be there to obtain the 0. Scalar multiple, that is scalar matrix cu must belongs to v, and c into u plus v equal to cu plus cv, c plus d into u is equal to cu plus du, and c du is equal to c du. So now let's have one question. Suppose we have r square but without the 0 vector, do we still have a space? The answer is no. Why? Because I said that in the field 0 vector must always be put there. So if suppose u vector belongs to the vector space, then 0 into u must also belongs to the vector space, that is 0 belongs to the vector space. So in all the vector space, 0 vector must be included. Okay. Now I have one interesting question. Which of the following are vectors? First example is very quite simple. You can just see like vectors is, and second is also a simple. Let's say it is a one component is this, second component, third component, and up to mth component. It is first, it is second component. Okay. So in this there are m components, and what can we say about this? In this there are 6 components, 1 2 3 4 5 6. So there, so it is also a vector. So matrix is can also be treated like a vector. I am not, because we can add, what we can do for vectors, we can add two vectors, we can multiply a vector by a scalar. Similarly, we can add two matrix, we can multiply a matrix by a scalar c, so it is will be ca. And for matrix to be in the vector space, it must also follow some other properties that we have seen earlier. And this is image can treat as a vector, as a matrix. So if matrix is a vector, then image can also be considered as a vector. Now fifth is polynomial. So polynomial, for polynomial, can we add two polynomials? Yes. Can we multiply a polynomial with a scalar? Yes. So it can also be treated like a vector, for which there is a one component of x ki power n, that's coefficient, one other coefficient, this. So it can also be treated like a vector. So all these, all five are vectors. Now what is a subspace? Subspace, it is a subset H of a vector space that itself is a vector space. So the elements in a subspace belongs to the vector space, but they itself is also a vector space. For these elements to vector space, it must follow these three properties. Because the subspace is also a vector space, so what I have said in vector space, the 0 vector must be there. So the 0 vector of v is in H, so it is true. Now H is closed under vector addition, that is if u and v belongs to vector space subspace H, then u plus v also belongs to the H. So this property must also be checked. And scalar multiplication, that is cu must belongs to H. So if these three properties are satisfying, then we can say that span of vectors is a subspace. For span, I am going to go forward. What is span? Now what can be the subspace of R square? So we have two components, as like we can say x or y. So I have written a line passing through origin. Why? Because the line passing through origin, that will be ax plus vy equal to 0. Just a minute. So ax plus by equal to 0. For vector space, we have to check these three properties. First is 0 vector must be there. So a into 0 plus b into 0 equal to 0. Satisfy. For second property, if u, that is if ax1 plus by1 equal to 0 and ax2 plus by2 equal to 0, then their summation, that is a. So x1 also belongs to the vector space. So second property is also satisfied. Third property is closed under multiplication by scalar. That is if ax So Cx comma Cy also belongs to the vector space. So this is a vector space, and for R3 we can say a plane passing through the origin will be a vector space. If suppose for R square, if the line does not pass through origin, then Ax plus By equal to 1, and 0 comma 0 does not satisfy, so not a, so Ax plus By equal to 1, not a subspace. Okay. Now what is span? Suppose vectors v1 v2 up to vn belongs to the vector space V, then span of v1 v2 up to vn is equal to a1 v1 plus a2 v2 plus a3 v3 up to an vn, where a1 a2 an all belongs to the field. Okay. Now there's one example. If v1 is 1 to 4, and v2 is equal to 4 6 3, then their span will be is equal to span of v1 v2 is equal to a1 v1 plus a2 v2. So it will be a1 plus 4 a2 2a1 4a1 plus 6a2 plus 3a2, like this. Okay. Now can we talk in terms of matrix or polynomial? As I said, the matrix and polynomial is also can be treated as vectors. So let we have two matrix of 2 1 0 0 0 and other is 0 1, then their span will be a1 a2 0 span is equal to a1 a2 so the matrix can also be treated like a vectors, and for polynomial also we can say like this. So now span of v1 v2 up to vn is the smallest subspace containing vi. Okay. For the subspace, first of all we have to prove that span of v1 of v2 up to vn is a subspace. Okay. So for subspace we have to prove three properties, that is it contains a zero vector, then span of v1 v2 vn is equal to a1 v1 plus so zero vector belongs to, because if a1 equal to 0 a2 equal to 0 all of these, then 0 belongs to span. Okay. One property is clear. Now other property, it contains all linear combinations, because span of v1 up to vn is equal to a1 v1, so we can say that it contains all the possible combinations which can be formed using v1 v2 up to vn. So second property is also satisfied, that it is closed under vector addition. Second, it must scalar multiplication. So if for v1 we can say that a2 equal to 0 equal to a3 up to an, so span of v1 up to vn contains a1 v1, it also contains a2 v2, similarly it also contains an vn. So we can say that it contains all the scalar multiplications of all the vectors. So we have proved that span of v1 of vn is the subspace, but now why it is the smallest? For that I will give you an example. Suppose I have a vector space of 1 0 0 and 0 1 0. So we can say that the span of this will contain a b 0. So it is a span of this is a, it is a vector, it is a subspace which is containing these elements. But there is also another possible, that is span of 1 0 0 0 1 0 0 0 1. What it will equal to? It will equal to a1, a2 and a3. So it also contains the these vectors, isn't it? Because if we keep a3 equal to 0, then a1 and a2 belongs to this this vectors, this subspace. But because we have to find the smallest, so we will only take the span of those vectors which are there, not because in this there are 3 linear independent vectors, and their span will also form a span of 2 linear independent vectors. Okay, so span of this will be now linear dependence and independence. Suppose we have n vectors, so if a1 we keep equal to v2, for linear independence, for this condition to be satisfied, a1 equal to a2 equal to a3 up to an all must be 0. But for linear independence, at least one is not equal to 0, ai. Okay, that is, we can write suppose vm vector as a linear combination of all the other remaining vectors. So that is why vm vector is dependent on other vectors. Now what is spanning set? If a vector space, suppose vector space is of Rn, that is n dimensional. So if v vector space is equal to span of v1 v2 up to vn, then v1 v2 v3 all vn is called spanning set. Just so we are taking an n dimensional vector space. So for creating the span of v1 v2 to a vector space, we definitely have n independent vectors. Those will be 1 0 0 dot dot 0 1 0 0 0 0 1 0 0. So the number of vector which is present in a spanning set will be n for n dimensional. So size of, okay, for spanning set of n dimensional vector space, and vectors must be there linear independent. Okay, and other is linear independent set. It is a collection of those sets which are linear independent. So for an n dimensional vector space, all n are linear independent, but if we take any two of them, then that will also be vectors, that will also be linear independent. If we take 3 only, then it will also be linear independent. So size of linear independent set is less than or equal to size of spanning set. Okay, so this property is also in a finite dimensional vector space, size of an linear independent set is less than or equal to size of spanning set. Okay, now basis the set of vectors which are linear independent and span of their subset. So we can relate it to a spanning set. Okay, because the span of their set is a vector space, and what is the definition? If vector space is equal to span of all those vectors. So for n dimensional, we must have n vector space, n vectors, and those must all be linear independent. So if we have a question like if someone ask a question for r square 100111, if someone asks that can these set of vectors can form the basis, we can directly say no, because for an n dimensional there must be n vectors only, and those must be linear independent. So if there are n minus 1, n plus 1 or something vector which are not equal to size, the number of vectors which are not equal to n, then we can directly say that they are not bases. So that is the insight. Now dimension of vector space. There is a number of linear independent vector, that is length of any basis of V. For dimension of vector space for Rn, dimension of vector space will be n, because the number of linear independent vectors will be n for n dimensional. Okay, now for dimension of subspace, number of linear independent vectors present in subspace of U. So suppose I have 3-dimensional vector space, but the vectors given to me is 1 0 0 and 0 1 0. So space will be a span of these two vectors. Vector space will be a span of these two vectors only. So the number of linear independent vectors in it is equal to 2. So dimension of subspace is equal to number of linear independent present in subspace of U. So here two vectors are present, so its dimension will be 2. Okay, now sum of subspace. Sum of two subspaces E and F written consists of all sums where U belongs to E, V belongs to F. It is the smallest of all subspace containing both the subspace. So basically we have to find the total number of linear independent vectors present in the span, because using them we can generate I have two subspace E and F. E containing span of V1 V2 V3, F containing span of, so we have to find the sum of spaces, and we have to find the span of those vectors. Span of, suppose it is V, then U1 U2 U3 up to UN, span of those vectors. Using them we can form E subspace and F subspace, both subspace we can form together. So we have to find those vectors. So suppose in E there are two linear independent vectors. In F 3 linear independent vectors are there. Then we have to check those independent vectors. Like in E there are 1 0 0 0 1 0, and in F there are, and then we are asked to find the E plus F, that is those number of linear independent which are present in either A, either B, or both. So it is like a union. So 1 is present in this 1 0 0 0 1 0, it is already counted, and this is also present. So number of linear independent vectors are 3. So it is also called as the dimension. Now intersection of subspace. In this, basically we have to find the total number of all those linear independent vectors present in span of u1 u2 up to un, as well as in span of v1 v2 and vn. So taking the same example as previous, so in E the vectors present are this, and in F these vectors are present. So we have to take those linear independent vectors which are present in both. So in E this is present, this is, and in F these. So the vectors which are present in both are 1 0 0 and 0 1 0. So dimension of E intersection F is equal to 2, that is number of linear independent vectors which are present in both the subspaces. Now direct sum of subspace. If u and w are subspace of vector space, then u plus v is denoted as if u intersection w is equal to 0. That is, if in one subspace 1 0 0 is there and other subspace, then u intersection F is equal to 0, because it is present in u, this is present in v, but their intersection does not have the common linear independent vectors. So then u plus w will be called as the direct sum. Now given a subspace of u of a finite dimensional, there exists a space w such that v is equal to u plus w. So we have already given a u and v, and we have to find the w, that the w will always exist in a subspace of u. Let's take Rn vector space. So in the subspace u, suppose 0 1 1 0 0 0 up to n times is there, and in w we want that their intersection is equal to 0, that is in w these two must not be present, and remaining them all this will be there 0 0 0 1 0. So if there are two vectors in it, then n minus 2 vectors will be present in this, and their intersection is equal to 0. So we can generalize this for r n dimensional. If m linear independent vectors are there in u, then n minus m is present in v, and so we can always write it v as a direct sum of subspace of two other subspaces. Similarly, we can do also subspace decomposition. Now there is one formula, but if you have understood all those previous topics which I have told, then you can also easily derive this. So dimension of u, number of linear independent vectors present in u, okay. Dimension of w, number of linear independent present in w, linear independent vectors. And dimension of u intersection w, linear independent vectors present in both u and w. So it can be treated like a Venn diagram. U w, dimension of u that is present in u, dimension of w that is present in w, and dimension of u intersection w that is present in both. And then we have to find a dimension of u plus w. It is like a union, which is number of linear independent vectors present in u or v or both u and v. So dimension of u plus w, that is union, is equal to dimension of u plus dimension of w minus dimension of u intersection w. Okay. Now there is one last question on the subspace, direct sum subspace. So here we have to find the dimension and basis of all those four vectors. First, w1 is equal to span of this, then first we write w1 as a matrix in the matrix form. 1 minus 1 3 3 0 we have to find the dimension of w1, that is the number of linear independent vectors present in w1, and it can be found using row echelon form by converting it by using row operations. Okay, so I am just writing the final answer by after converting this matrix into row reduced form. It will be 1 0 0 0 1 0 2 1 0 and minus 5. Number of linear independent vectors present in W, dimension of W, is equal to 2. Which what are those? Where are those vectors? First is this and second is this. Okay. Now we have to find the basis. Basis is the from which vector these independent vectors are created. It is created from first vector and second vector. So basis is equal to 1 minus 1 3 and 3 0 minus 3. There can be other bases also, because bases are linear independent, so we can use second and third also, because these two are linear independent. How? A times 0 1 0 so A is equal to 0 and B is also equal to 0. So basis can also be this and this, basis can be this and this also, because these two are also linear independent. So there can be so many bases, so you can choose accordingly whichever you want. Now we have to find the for W2. Similar procedure will be using. So dimension of W2 will come as, just a minute, by converting it into row reduced form, it will be so first and third. So dimension of W1, it is dimension of W2 is also equal to 2. Now, and the basis can be first and second, and first and third, second and third, all can be the basis. Now dimension of so we have two choices. We can find this using two methods. First method is we can just check how many linear independent vectors are common in U and W both, in W1 and W2. So in W1 and in common or present in at least one. So 1 0 0 is present in first and second both. So 1 0 0 is present in at least W1 or W2. 1 0 1 0 is present also, and 0 0 1 is also present. So dimension of W1 plus W2 is equal to 3. And for this, which vectors which will form the basis? First, second of W1 and second of W2, because these three are linear independent. And for dimension of W1 intersection W2, we have to find those number of linear independent vectors which are present in both W1 and W2. So in W1 and W2, which are present in W1, these two 1 0 0 and 0 1 0, and in W2 0 1 0 0 and 0 1. So present in both is 1 0 0. So dimension of W1 intersection W2 is equal to 1. And we can also find this using formula, like dimension of W1 plus W2 is equal to 2 plus 2 minus 1, that is 3. So the formula is also proved. So that's all from my side. Thank you and have a nice day.